Our last speaker, Ms. Kyriaki KALAINTZIDOU.
Good evening. This presentation is about nutrient removal, not hazardous removal. It's about phosphorus removal from wastewater effluent. Why is there such a concern about phosphorus? It's because phosphate rock is constantly diminishing, which is the main source of phosphates, and because the excess use of phosphates has led to eutrophication. For this reason, we must find a way to find another source of phosphates to re-enter in phosphate cycle. Phosphorus in wastewaters is presented in large quantities, and for this reason, a lot of removal treatments are being used currently. There are physical, chemical, and biological technologies. The regulations are getting stricken while time passes, and for this reason we must remove, but in this project the aim was not only to remove, to recover also phosphate in a utilizable form. The outline of the experimental part of this study was includes preliminary experiments that were conducted in tap water. Then, according to the results derived from these experiments on the secondary effluent of the wastewater treatment plant NIA, which is treating the waste of the touristic area of Thessaloniki, was used for evaluating chemical precipitation. The wastewater treatment plant secondary effluent was used for the adsorption, and then after the saturation of the adsorbents, the regeneration solution was used to precipitate phosphates. Finally, the precipitants were evaluated for their bioavailability in soils. From the chemical analysis for the water used from the area of Thessaloniki and from the secondary effluent from the wastewater treatment plant NIA, we must notice the high concentrations of calcium and magnesium and the low concentrations of ammonium present. The reactions used for the chemical precipitations were magnesia, calcium hydroxide, huntite, ferrichlor sulfate, and sodium aluminate. The residual target concentration for the effluent selected was the one for sensitive areas, which is 1 mg phosphorus per liter, and these reagents were used in order to precipitate insoluble phosphate salts. From the results of the precipitation, we can notice, I don't have a pointer now, that at high pHs, the results from magnesia, calcium hydroxide, and huntite are similar to the ones that derived from increasing pH using sodium hydroxide itself. For ferrichlor sulfate and sodium aluminate, decreasing pH favors precipitation. We have noticed that the 90% of the precipitation proceeds the first 10 minutes. Efficient removal for calcium and magnesium salts occurs at pH greater than 9, and this probably happens because of the high content of calcium and magnesium tap water has already. Efficient removal by iron and aluminum ions occurs at a pH range 6 to 8. Using the secondary effluent, initially we attempted to precipitate stuvite. Stuvite is a slow-released fertilizer, but its formation was not feasible because of the low content of phosphates the secondary effluent has. The content of phosphates is around 5 mg phosphorus per liter. This demands high quantities of ammonium and magnesium, and the addition of these high quantities result to higher quantities at the effluent for the ammonium and magnesium disposal limits. So stuvite was not precipitated. From the experiments of chemical precipitation, we can see that we selected a pH of 10. For this reason, we added high quantities of the reactions, but in some cases we needed to add sodium hydroxide too. We can see that we achieved efficient removal of phosphates, but the percentages of phosphates in the precipitants are really low. At the end of the process, we must decrease pH to 9 because the disposal pH range is 6 to 9. Elevating pH in the beginning of the process and decreasing pH at the end of the process elevates the operating cost of the whole process. Chemical precipitation for iron and aluminum ions took place at the pH of the secondary effluent. We have efficient removal in the case of iron, but not in the case of aluminum. We can see that the percentages of phosphates at precipitants are high, and this encourages our further studies of bioavailability of the precipitants. The operating cost for these processes has the lowest cost for the addition of sodium hydroxide and for ferric chlorosulfates, and at the same time we have high percentages of phosphates at the precipitants. We continue with the procedure of adsorption. The adsorbents used were iron-based oxyhydroxides, commercially available GFH, bioxide, and Aqua Zero, and lab-synthesized iron oxyhydroxides. We also used, in order to compare, a commercially available resin by pyrrolite. If our adsorbent has this surface area, and we can see the surrounding of anions in the wastewater, we can see that iron is selective to phosphates because of the affinity iron has with phosphates. From the breakthrough curves derived from the implementation of rapid small-scale column tests of the adsorbents that simulate full scale, we can notice that we have high adsorption capacities for all of our adsorbents, especially for the lab-synthesized ones. After the saturation of the adsorbents, desorption took place with implementing alkaline solution of sodium hydroxide. This allows the multiple uses of the adsorbent, and it also pre-concentrates phosphates in the regeneration solution, which can be further used for the precipitation of phosphates. As we have already seen, phosphates precipitation by calcium and magnesium is favored at high pH values. The regeneration solution has a pH value around 12.3. This makes it ideal to precipitate phosphates. After the precipitations, we can notice that the percentages of phosphates at precipitants are really high. For the calcium phosphate salt, it's around 17%, and for the magnesium phosphate salt, it's around 6.4%. We continue with the bioavailability tests, and we can see that from the charts that both magnesium and calcium phosphate salts have good release in soil in a duration of 5 days. On the contrary, for the iron phosphate salt, we have a slow release in soil for the in the basic soil, and slow to zero release for the acidic soil. We can conclude that for calcium and magnesium phosphate salt, they can be used as fertilizers. After the experimental study, a pilot plant was implemented at the wastewater treatment plant in EA. We can see that at place 1, the secondary effluent is filtrated through membranes. Then the effluent feeds the adsorption column. And after the saturation of the column, we have its regeneration. We take sodium hydroxide from here, and it's implemented in the solution. And then we have the chemical precipitation here. And after the precipitation, the sodium hydroxide is filtrated through membranes too, and it's recycled and reused. The precipitant is collected at this place. From the pilot plant, we have the breakthrough curve that shows almost shows similar adsorption capacity to the lab scale results. Is around 4 milligrams phosphate per gram of the adsorbent. While generating the adsorbent at the pilot plant, we had some problems, and through the optimization process, we concluded that we need to implement higher pH values at the beginning of the process in order to achieve the generation. We have also collected the precipitant, and we can see that it has a high concentration of phosphates, it's around 12%. And from the XRD pattern, we can see that it is consisted mainly from hydroxylapatite. It must be further examined for its bioavailability too. To conclude, we can see that we have efficient removal by ferric chlorosulfate, but iron phosphate has a slow release in soil. We can achieve high adsorption capacities by using iron oxyhydroxides, and by regenerating the adsorbent, we can also use the adsorbent for multiple times, and the regeneration solution too. The regeneration solution is ideal for precipitation by calcium and magnesium salts, and the calcium and magnesium phosphate salts that are precipitated can be used as fertilizers. We have encouraging results from the pilot plant, and we hope for a full-scale application. Thank you very much for your attention.